Okay, I thought I'd take just a few minutes to go through this flow chart with you guys in case you are interested in using it. I already posted the completed version, but here is how it got that way. So the big picture, the overall function of the cardiovascular system is, remember, to ensure adequate blood flow to capillary beds. And what we said before at the very first lecture over cardiovascular system is that blood flow is basically F equals delta P over R. Here is the pressure, and here is the resistance. So the difference in the pressure between 2 points would be delta P. And resistance, remember, is the opposition to flow between 2 points at any given pressure difference. So then we started to break it down. And we said that when you're dealing with pressure, there's basically three things to consider. The cardiac output, what the heart is doing, is the primary thing that generates pressure. And then you can impact pressure also by blood volume changes, which are going to be primarily related to the kidneys. And then with what the vessels are doing. And the vessels can increase or decrease resistance and therefore change blood flow patterns. And then what we did last time was concentrate on this part, which is cardiac output. And we said that cardiac output was basically an interaction between stroke volume and heart rate. And then we broke down stroke volume. And stroke volume was how much blood leaves the ventricles per contraction of the ventricles. And so what we said is that there were two things that positively impacted stroke volume and one thing that negatively impacted stroke volume. I want to remind you that whenever you see something that's in red, it's exclusively a negative impact, not bad, but reducing impact. And whenever you see green, it's going to be a positive impact. So we said that afterload was what the pressure that the ventricles are pushing against. And afterload has directly to do with how much pressure is in the arteries. So, for instance, if you vasoconstricted or constricted your aorta, you would increase afterload, and then at the same pressure, not as much blood would leave the heart. So please note also that there is a direct relationship between the concept of resistance and afterload. Whenever something is put in a dashed line, it means it's kind of a secondary impact, and all of the primary impacts are in solid lines. Okay, so afterload reduces stroke volume. Let's do the other simple one. Ventricular contractility is how hard the ventricles contract. And we will see that they can contract harder when you stimulate the wall of the ventricles with the sympathetic nervous system or with hormonal epinephrine. So ventricular contractility makes the ventricles contract harder, which of course increases stroke volume. And then EDV is the one that confuses people. EDV is end diastolic ventricular volume. It is the volume including both the fluid and the size of the chamber in the ventricles at the end of diastole just before systole. And so there are a couple things you consider with end diastolic ventricular volume. You say that preload is how full the chamber is, and how full the chamber is affected by filling time and atrial pressure. Atrial pressure is both how full the atrium is and also how much the atrium actually contracts. That will contribute to preload, which is what's going to be in the ventricles. Filling time will also contribute to preload. And of course, filling time has a relationship to heart rate. It's not exclusively positively or negatively, so it's in a black line here. And then the only other thing that we talked about here was this whole concept of Starling's law, which impacts EDV. And Starling's law says that there is a sarcomere length at which the cardiac muscle sarcomeres are sort of optimal, and then they will actually contract better. And so Starling's law says basically that a full ventricle will get a better contraction and a bigger stroke volume than an empty ventricle, because you get the length and tension of a myocardial sarcomere at a more ideal length and tension. So how do we impact these things? Well, the skeletal muscle pump is using your skeletal muscles to aid in what we call venous return, which will stretch the cardiac muscle a little better, and that will add to EDV, which will add to stroke volume. Same thing with the respiratory pump. That's breathing in, which increases the pressure in your abdominopelvic cavity and decreases the pressure in your thoracic cavity. Um, and that squirts the blood up and helps with venous return, which of course stretches the cardiac muscle cells, sarcomeres, and adds to EDV. Note that there's also a relationship between these two and the concept of venous return directly to preload and directly to atrial pressure. This just says if you're doing more of these, you actually increase the amount of blood that's in the atrium because of venous return. And if you're doing these, you're also going to, of course, directly impact the preload. So there's this relationship, and then there's also this relationship. Okay, so that's stroke volume, and these are the ones that people have a little trouble with. And then we can talk about heart rate, which is actually a little easier. So with heart rate, basically the two primary ways that you're going to control it is with the nervous system. The nervous system can change the rate at which the pacemaker cells will depolarize. And then you can also do some hormonal control. So let's look at this for a second. Okay, so the rate of depolarization in pacemaker cells, remember that without the nervous system attached, they depolarize about 100 times per minute. But please note that with sympathetic innervation, it's going to increase the rate of depolarization. Same with hormonal epinephrine, right, which would of course been released because of sympathetic stimulation. So that would increase the rate of depolarization and therefore increase the heart rate. What about parasympathetic innervation? Parasympathetic innervation from the autonomic nervous system will decrease the rate of depolarization and therefore decrease the heart rate. So this is one of the hormones. Remember, we also said that there was one other one. Thyroid hormone has a positive impact on heart rate. Not super dramatic, but pretty consistent. So, and then to go back, remember this whole ventricular contractility that we talked about? That was because of what the sympathetic nervous system is doing or hormonal epinephrine is doing. And then we said that the hormonal epinephrine is an example of hormonal control. Of course, it was started by nervous system control, but okay, so we have done all of this. We haven't done these other things that I'm going to talk about, but I'm going to go ahead and tell you now so that you'll have one video that you could use to review this flow chart if you decide to use it for studying. I think I told you guys this in class, but the flow chart is actually not different information than the information we have in lecture or in your notes. It's just a different way to present it. Okay, so I want to go from here and look at the ways to turn on the autonomic nervous system. And so in addition to the whole tiger being in the room idea, there are also other ways to turn on the autonomic nervous system. They're what are called the baroreceptor reflexes, and baro implies pressure. And so the story here is that if you detect high pressure in certain places in the body, you can use that to decide whether to turn on the sympathetic or the parasympathetic nervous system. And so with the baroreceptor reflexes, let's look at the arterial ones first. Okay, so basically you have baroreceptors or pressure receptors in the aortic arch, which of course is leading to all of systemic circulation, and also in the carotid sinus. And the carotid sinus mostly is really controlling blood pressure to the brain, because 75% of the blood flow to the brain comes through the paired internal carotid arteries. So what happens in these should make sense to you. If, for instance, you detect pressure in these that is too high, then you are going to send that sensory information in and then decide, based on that pressure that is too high, to turn off the sympathetic nervous system and on or up the parasympathetic nervous system, which would of course help you to decrease that arterial pressure that was too high. Likewise, if you detect arterial pressure that was too low, Then you're going to send that sensory information and ultimately use that to decide which branch of the autonomic nervous system to turn on. If the pressure was too low in the arteries, then you would turn on the sympathetic and off the parasympathetic. And that, of course, would change the rate of depolarization and also increase the heart rate. Okay, so we have another baroreceptor. So this one's very different than these two. These are arterial baroreceptors, and they exist in the aortic arch and the carotid sinus. This one is a right atrial baroreceptor reflex. And so I will talk about this again in class, but I'm going to just tell you what this one does. This is assessing pressure not in the arteries, but in the right atrium. The right atrium is, for all practical purposes, the end of systemic circulation. It's when the blood has been returned. And so if what you detect is high pressure in the right atrium, then you use that sensory input to decide whether to turn on the sympathetic or the parasympathetic nervous system. And so you got to think about it this way. If you have more blood going to the right atrium, then you want to assess what to do about it. Well, you don't want to turn on the parasympathetic nervous system because that would further slow down the heart rate. The venous return is already really high, so we don't want to slow down the heart rate because then you're going to end up with a congestive heart failure type situation. So all of this blood that's going to the right atrium means that I actually need to pump more frequently or harder. And so what I would actually do with high pressure in the right atrium is turn on the sympathetic nervous system and down the parasympathetic nervous system. So I think of these two baroreceptor reflexes. This one is a front end baroreceptor reflex because it happens in the arteries right as they leave the heart. And this one is a back end baroreceptor reflex because it happens in the right atrium when the systemic circulation is almost done. So front end and back end. Now, if that doesn't make sense to you, then we will talk about it again in class, and it probably will. Okay, so that's sort of the nervous system part of the story. And then all we have left to do is sort of talk about vessels and talk about the kidneys. Okay, so one of the other ways to regulate blood pressure and therefore blood flow is with what the kidneys are doing. And so blood volume is regulated primarily by the kidneys. Of course, some of it you sweat out and lose by other fluids, but primarily it's what's happening at the kidneys. So what do the kidneys do? Well, the kidneys kidneys actually either secrete or respond to a few different hormones. EPO, we know that the kidneys actually secrete erythropoietin, which can cause red blood cells to be made via erythropoiesis. And we also know that ANP or ANF, which comes from the heart, can make the kidneys lose more water. So, of course, that would decrease your blood volume and therefore your blood pressure. And then the other one that we've already learned is ADH, and ADH comes from the posterior pituitary, and it's an antidiuretic hormone, so it causes water retention or conservation at the kidney. And then this one we haven't really done very much yet, but we're about to. It's called renin-angiotensin. And this is one of the mechanisms that will actually be really effective at increasing blood pressure. So what's going to happen is when the kidneys detect low pressure in the afferent arteriole, they'll release some chemicals that will ultimately end up causing the release of aldosterone. And aldosterone, of course, causes water and sodium conservation and will increase blood pressure. In addition, they will also have an impact on vessels. Angiotensin, not this one, but angiotensin 2 is the most powerful vasoconstrictor in the body. So this is all kind of hormonal ways in which the kidneys can change the blood volume and therefore change the blood pressure. And then the last bit of the story is just this, and that is peripheral resistance, the resistance that we talked about. So how resistant to flow how resistant a vessel is to flow between 2 points at a given pressure has to do with the elasticity of the vessel. So if it doesn't have good snapback, it's not going to flow very well. Has to do with the length of the vessel. That's what we talked about. If you gain like 30 pounds, then your vessels are longer and there's more resistance between 2 points, between point 1 and point 2, if point 1 and point 2 are further away from one another. And then also the viscosity of the blood. If the blood is really viscous, it actually provides more friction and adds to resistance. And then the other thing is the vessel diameter, and both inherent vessel diameter and then the capacity for vasoconstriction and vasodilation. So if you want to impact pressure, you can do it several different ways. One of the ways is changing vessel diameter. So I'll tell you a couple of different ways that you can change vessel diameter. The sympathetic nervous system actually can cause vasoconstriction or vasodilation, so the sympathetic nervous system can do that. Hormonal epinephrine can also cause vasoconstriction. Usually it's more vasoconstriction than vasodilation in these two locations. And then this hormone right here, like I said, we will talk about angiotensin II specifically, but angiotensin II is the most powerful vasoconstrictor in the body, and it will actually be able to change vessel diameter, which impacts resistance and therefore impacts blood flow and also impacts blood pressure. Okay, so that is the whole story, and when you shrink it down, it looks like this. It's the same story that we told, or we are going to finish on Monday on lecture. And you guys have a quiz on Monday. It only covers the part of this that we already have covered in class. I just gave you a full overview of the whole thing. Okay, I will see you guys then.